Okay, so now we're gonna go over section 5.2, which is about the definite integral. So after going over areas in 5.1, now we're gonna talk about integral, definite integral. We're gonna define what we mean by definite integral and how is definite integral related and how is it different from x under a curve. Okay, definition. Let f be a function. Define, so we don't need continuity. When we did areas, the function had to be continuous and non-negative. This is a rather loose requirement, just define over AB. That means you can plug the brand in and get a y value. No continuity is needed. Then the definite integral, of f over AB is a definite integral. That's how we write it down. Dx, that means with respect to x, it's the limit as n goes to infinity, sum of ci delta x, I equals 1 to n. Same definition as the area. The only thing is, in the case of the area, the functions had to be non-negative. Here the functions only have to be defined. These are called Riemann sums. This is after the German mathematician Friedrich Riemann, who actually came up with those Riemann sums. Remember, lower sum, upper sum, the CI be anything. Where's CI? Provided the limit exists, of course. Provided the limit exists, where the CI, you can pick any value. It doesn't have to be left endpoint or right endpoint. It could be anything, okay? A is called the lower limit of the integral, and B is called the upper limit. And it's called definite integral. Definite integral. Remember what we did in 5.9 was indefinite integral, which is antiderivative. It had no limits. This one has lower limit and upper limit. It's defined as the limit as n goes to infinity of all these Riemann sums, which is similar to the upper and lower sums, except the CI here could be anything in the interval. It doesn't have to be left or right value. Now, if this limit exists, then we say f is integrable over AB. If the limit exists, we say f is integrable over AB. Okay, number 4, page 394. Number 4, page 394. It says evaluate the Riemann sum for f of x equals 1 over x, where x is between 1 and 2, with 4 terms, using right endpoints. So between 1 and 2, you want 4 subintervals. So you're gonna, delta x is b minus a over n, which is 1 over 4. So that's 1, and then it's a quarter more, another quarter, and then 2. There's 4 subintervals in there. So the Riemann sum of f of ci delta x, I equals 1 to 4. It's right endpoint, so it's f of 1.25 times 1 over 4 plus f of 1.5 times 1 over 4. So f of 1.75 times 1 over 4 plus 2 times 1 over 4, which is going to be 0.634 524. Okay, and this gives me an estimate for the area under the curve. For part B, it says you use the midpoints as sample points, midpoints. So instead of using right endpoints, we're going to use midpoints. So what's the midpoint of 1 and 1.25? You add them up and divide by 2. So 1 plus 1.25 divided by 2, so that's 1.125, and then 1.25 plus 1.5 divided by 2, 1.375, 1.5 plus 1.75 divided by 2, 1.625, and then 1.75 and divided by 2, that's 1.875. So we're going to use these values instead of the right endpoints. So sum of f of ci delta x from 1 to 4, it's f of, it's 1 over 4 times all of them, so it's f of 1.125 plus f of 1.375 plus f of 1.625 plus f of 1.875, 0.691220, okay? 0.691220. Just estimating the area using different values. Now, so remember, if the limit exists, we say that function is integrable. We know if the function is continuous, if the function itself is continuous, like when we defined area, then it's integrable. And that's all we need to know. So continuity implies integrability. Continuity implies integrability. So meaning if f is continuous over AB, if f continuous over AB, or it might not be continuous, it might have a finite number of jump discontinuities if f has a finite number of jump discontinuities, then f is integrable over AB. So to t that definite integral to list, the function has to be continuous. If it's not continuous, it may or may not exist. So let's look at number 20, page 394. At number page 394. It says, express the limit as a definite integral on the given interval. So how do we express the limit as n goes to infinity, I equals 1 to n, xi square root of 1 plus I cube delta x over 5. Well, you can see this is my f of ci, and this is delta x, and this is a and b. So the integral from a to b, f of x, which is x square root of 1 plus x cubed, and then delta x becomes dx. As simple as, we're not evaluating, we're just writing the limit of the Riemann sums as a definite integral, so we can get used to that. Okay, now some properties of the summation notation. Properties of sum notation. The first property is the sum from 1 to n of c equals nc or cn, for example. If I'm adding 5, 10, 5, so it will be 5 plus 5 plus 5, 10 of them, right? As many as that number is. So 10 5s, which is 50. Same thing here, okay? The sum from 1 to n, CAI equals, so you can pull the constant out. AI is a variable because I is changing. That's the index. I mean, sort this out. This is actually CA1 plus CA2 plus CAN. You can factor the C out, which will give you that. Okay, so if you have a constant inside the sum, you can pull it out. Number 3, the sum of AI plus bi equals sum of ai plus sum of bi from 1 to n, which is common sense because that's going to be what? a1 plus b1 when I equals 1, a2 plus b2 when I equals 2, and then an plus bn when I equals n. You can add up the a's, you get this. You can add up the b's, you get that. Okay, and if it was minus, same thing, you can pull the negative out. Number 4, sum of I from 1 to n is n plus 1 over 2. So basically what this is saying, if I'm adding the first n counting numbers, okay, the first like 100,000, whatever, it's how many you have times 1 more divided by 2. For example, if I am adding the first 100 counting number, it's going to be 100 times 100 plus 1 over 2, which is 50 times that, 5050. Pretty neat. Okay, and of course it's not hard to prove it. Same thing with the sum of the squares, I square from 1 to n. If you're adding 1 square plus 2 square plus n square, it's their number times 1 more times 2n plus 1 all over 6. And the sum of the first cubic counting numbers is n square, n plus 1 square over 4, which you can write it as n plus 1 over 2 all squared. So you can see where it looks like that one. We're going to need these to evaluate definite intervals using the limit process. So let's talk about that. So there's always a test question similar to this. Always evaluate using the limit process. Well, when we do the fundamental theorem of calculus, we won't have to do the limit process anymore. But for now, remember in calculus, everything goes back to limit. Everything. There wouldn't be calculus without it. So this is, remember, this is the limit as n goes to infinity of the Riemann sums. F of ci delta x. Delta x is always b minus a over n, which is 1 minus negative 2 over n. We don't know how many intervals, okay? And ci is, we're going to use a plus I delta x for simplicity. A is negative 2, I is I, and delta x is 3 over n. So it's negative 2 plus 3i over n. That's ci. So we need f of ci. It's f of negative 2 plus 3i over n. We're going to plug it in. This is f of x. So it's 2 times negative 2 plus 3i over n square minus 3. This is f of ci. And we're trying to work this out. So we did delta x. We did ci. Now we did f of ci. Now we're going to do the sum. So the sum from I equals 1 to n, f of ci delta x equals sum from 1 to n, 2, and then if we FOIL that, we get 4 minus 12i over n plus 9i squared over n squared minus 3. So that's f of ci, and then we're going to times it by delta x, which is 3 over n. So this equals the sum from 1 to n. We have 8 minus 3 is 5. I did that minus 3, and then minus 24i over n, and then plus 18i squared over n squared. We're going to times this by 3 over n. So distribute that from 1 to n. 15 over n minus 3 times 24 is 72i over n squared. 54i squared over n cubed. So we're going to split it up. So sum from 1 to n, 15 over n minus 72 over n squared is a constant. So let out. We're going to pull this out as well. Sum I from 1 to n. And then 54 over n cubed is a constant because only I is changing. 54 over n cubed. Sum of I squared from 1 to n. So if you bring that out, 3 over n, and that's 1 times n, which is n. 72 over n squared. Remember we just talked about these formulas. Sum of I is n plus 1 over 2. And then 54 over n cubed. Sum of I squared right there. It's n plus 1 to n plus 1 over 6. Over 6. So that cancels that. So the integral from negative 2 to 1 of 2x squared minus 3 dx is the limit, as again time goes to infinity, all of these, 15 minus, that's 36, n into n plus 1 over n squared, plus, that's a 9 n plus 1 to n plus 1 over n cubed. So the limit of a constant minus. Now remember, when s and n is infinite and we have a fraction, we only pick the highest power. If you look over here, this is 36n squared plus 36n, so we ignore that. 36n squared over n squared is 36. Same thing here. You have 9n times 2n, which is 18 cubed. Everything else is going to be smaller power. Over n cubed is 18. And the answer is negative 3. And can we get a negative for definite integral? Absolutely. Actually, we can check that on the grapher. So if you go to y equal, I'm just deleting what's in there. The function is 2x squared minus 3. Graph it. And then if you do second calc, and then you want to do the number 7, the lower limit is negative 2 nr, the upper limit is 1 nr. It will show you what you just did, and it gives you the answer. If you can't see it, it's negative 3. You can see what we find it's negative because the value underneath the x-axis, which is the negative value, is more than the value above the x-axis. And we're not finding an area. If we were to find an area, the function has to be positive. So this is just definite integral. Now I want you to do the same exact thing that I did in this example for example on page 9 star. I left it for you to work out. Okay, so I might have something like this on the test. Next. So remember we defined area under curve using limits, Riemann sums, but the function had to be positive. Now we're going to define area under a curve using definite integral. Area under a curve using definite integral. So if y equals f of x is non-negative. Okay, can't talk about an area if the function is negative, non-negative, and continuous. Okay, because to find area we need continuity over a closed interval, because we want to use the extreme value theorem over b. Then, so we're talking about a function that's positive and that's closed interval ab. If we want this area, then the area under the curve over the closed interval AB is the definite interval. And remember, this has to be greater or equal to 0 to get an area. Okay? Now, if f is non-negative, if f is not non-negative, if f is not non-negative, which means could be positive, could be negative, is not non-negative over AB, then I make sure it's positive, so we're gonna put absolute value. Okay, can't do area if the function is negative. Let's look at 36, page 396. 36, page 396. It says the graph of G consists of two straight lines and a semicircle. Evaluate each integral by interpreting it in terms of an area. So part A, you need to be looking at the graph. We want integral from 0 to 2 g of x dx. If you look at g of x between 0 and 2, it's a line. So we're finding the area of the triangle, which is 1/2 base times height. 1/2 base times height. So base is 2 and height is 4. So it's 4 square units. Okay, part B. Again, you need to be looking at the graph. Integral from 2 to 6 of g of x dx. From 2 to 6, it says in terms of area. So from 2 to 6 of g of x dx, we want the integral. The area is positive, but if you want the integral, the area is pi r square. It's half a circle, so it's half pi r square, but it's negative because it's underneath the x-axis, so negative 1/2 pi 2 square, which negative 2 pi. Remember, this is the value of the integral, it's not the area. If we wanted the area, it would have been positive 2 pi, because we would have to flip it. And part C, from 0 to 7 of g of x, 0 to 7 of g of x. From 0 to 7. So we already got from 0 to 2, and we got from 2 to 6, and then we're going to do 6 to 7. That's what we're going to do. So from 0 to 2, which is already, what was from 0 to 2? 4. And then from 2 to 6, we got negative 2 pi. And then 6 to 7, it's that small triangle, half base times height, which is 4.5 minus 2 pi. It's just areas of geometric figures, that's all. But if it's underneath, then it's negative because we're doing integral, not area. So here's a handout, page 11, just the difference between area and definite integral. Area, the function has to be non-negative, it has to be continuous, and the area is the limit of f of ci delta x, which is the definite integral, and area is always positive. In the case of an integral, the function has to be defined. It doesn't have to be continuous, it doesn't have to be greater or equal to 0. Same formula, you can see, same formula, but the answer may be negative here. Okay? Could be anything, because you're finding above and below the x-axis, okay? Another thing, this is not something I would ask about, but this is just sufficient conditions for a function to be integrable. So what do we have to say the function is integrable? If it's continuous, we already saw that. If it's bounded, like if the y value is between two values, then it's integrable. There's an example. And on the next page, if it's not bounded, then we know the function is not integrable, okay? So now properties of the definite integral. Definite integral is defined using Riemann sums, so whatever works for Riemann sums, it will work for definite integral. The integral from b to a f of x dx is the opposite a to b. Why is that? So once you flip these, you get a negative, because if you do b to a, this is a, b, so your delta x is negative, right? But if we go this way, delta x is x1 minus x0, delta x is x2 minus x1. If you go this way, delta x would be xn minus 1 minus xn. So it's the opposite of all these delta x's that you end up with a negative. Okay, that's how you end up with a negative. So once you flip the upper and lower limit, then you get a negative for the definite integral. So for example, if the integral from 0 to pi of sine to the fourth part theta d theta is 3 pi over 8, then the integral from pi to 0 of sine fourth d theta is negative 3 pi over 8. Okay, once you flip that, you get the opposite. Okay, the second property, if the lower limit and the upper limit are the same, the answer is 0. Why? Because if A is B, there's no area, okay, to find. That's why. So the integral from 1 to 1 square root of 1 plus x squared dx is 0. Just like Riemann sums, if you have a constant inside, then you can pull the constant out, just like Riemann sums. So for example, if you're doing integral from a to b of negative f of x dx, you can pull the negative out as well, because negative 1 is a constant. Okay, any constant pull out. Just like Riemann sums, the integral of f of x plus or minus g of x can be split up, because it's limits of Riemann sums, so it might as well. A to b g of x dx. And number 5, integral from a to b of x dx plus b to c, as long as these values are the same. Upper limit of the left is the same as the lower limit on the right. F of x dx, we can write it as integral from a to c f of x dx for any order of a, b, and c. They don't have to be in increasing order or decreasing order. They can be in any order. Like they could be c, a, b, and it would still work. From a to b, it's from b to c, because that's backward, so it's a negative, and then plus a to c. Okay, you can check that out. Let's look at 58, page 96. Let's look at 58, page 396. It says if integral from 2 to 8 f of x dx equals 7.3, integral from 2 to 4 f of x dx equals 5.9. Find integral from 4 to 8 f of x dx. Well, we know the integral from 2 to 4 plus, we just talked about this, 4 to 8 is going to equal integral 2 to 8, right? As long as these are the same. So 2 to 4 is 5.9 plus 4 to 8 is what we want to find. This is my n. A to 8 is 7.3. So A is 7.3 minus 5.9. 1.4. Okay, A is this integral. Okay. Alright, next property, if f of x is less or equal to g of x, their integrals behave the same way, because again they're Riemann sums. Less or equal to g of x over ab, then the integral of f of x dx a to b is less or equal to the integral a to b g of x dx. And the rest we talked about. 7 it's an area, and 8 is Riemann sum. It is lower sum and upper sum, so I don't need to do these anymore. Now I want to go over 72 before I finish this, page 397. Number 72, page 397. Use the property 8 of integrals to estimate the value of the integral. So how do we estimate the integral from 0 to 2 of x cubed minus 3x plus 3 over 0 to 2? Actually, they want us to do property 8, which I just showed you, but I didn't go over here. So if f of x is between, remember we did lower sum and upper sum. If f of x is between m and little m and big M, then m times b minus a is less or equal, because these are two rectangles. So basically, what we're saying here, if f of x between two values, between y equals m and y, this is y equals f of x. This is common sense. And y equals big M over AB. Then what this says, it says if you take the rectangle formed by M and B minus A, M times B minus A is less or equal, the area under the curve of f of x is less or equal to big M times B minus A, big M times B minus A. I mean, it's common sense. Okay. So if you look at the example that we have to use property A to estimate, we want to estimate this x cubed minus 3x plus 3 dx. So f of x is x cubed minus 3x plus 3 over the interval between 0 and 2. So if you find the derivative, you get 3x squared minus 3 equals 0 if x equals plus or minus 1. Well, x equals 1 is in the interval 0 to 2. So we know that f of x is greater or equal to 1 and less or equal to 5 over the interval 0 to 2. So if you do 1 times b minus a is less or equal, integral from 0 to f of x dx is less or equal to 5 times b minus a. So the integral is between 2 and 10. The integral is between 2 and 10. Again, the reason I got these is, I mean, I don't know if you see that or not. When c is 1, f of 1 is 1. When c is 0, I'm doing the endpoints and the critical value to find the maximum and the minimum. Remember the extreme value theorem? So f of 0 is 3 and f of 2 is 5. 8 minus 6 plus 3 is 5. So that's why I use max and minimum. Okay, that's where this came from, if you're wondering. And that's all we have to do from this section until 5.3. See you.